Okay, well,
What are you
welcome
talking
to
about,
the
Willis?
tutorial on
That him!
reactions of alkenes. And so we're going to start talking about alkenes and the fact that there is a very common way that they react. And so if we were to just draw some generic alkene just like so, right? And so if I were to treat this with an acid, then what we can see is that if we were to look at how these react, we have a dipole here where this hydrogen is going to be a partial plus and this chlorine here is going to be a partial minus. And so what's going to happen is the negative charge that is inside of this arrow, or this double bond here, so this has a center of negative charge. And the reason why this here has a center of negative charge is because if you look at a sort of molecular orbital picture of this, we have our pi bond that, remember, is above and below the plane, like so. And we have this bond that's in here. This is our pi bond that's here. It's this pi bond that we're going to have attacking this center of positive charge, which is over here by this hydrogen. So if we were to kind of come back now and let's draw an arrow here, we would draw the arrow from the center of negative charge, which is this area right here. And so this guy is going to go and pick up this hydrogen that's right here. But now that this hydrogen is being attacked, right, its electrons that are in between this bond here need to go to the halogen. So they're going to move over here, over to the halogen that we have. And so we draw this now representing something that looks like this. Whereas, let's just say here, we have the hydrogen, and at this point right there, we now have a positive charge here because this carbon only has 3 bonds, right? So only 3 bonds that are here, and so this is a carbocation. Okay, so now the next thing that we notice is that we have this carbocation, but we have already broken this hydrogen Cl bond. The Cl has picked up the 2 electrons that are in this bond. So we have Cl minus now that's hanging around right there. And so, of course, the next thing that can happen is for this negative charge area here to come over here and attack where this chlorine is, or the positive charge is there. So this now gives us this guy, and now we have this. So this is sort of the general way that alkenes react. And we're going to see this trend with many different types of reagents. Now, so what I want to kind of do is just give you a sort of generalized view of this. And so again, if we have our alkene that, say, looks something like this, so of course we have all those methyl groups there. We have A, and then it's bonded to B, so it doesn't really matter what this is. And essentially every time you're going to have this. Remember, we have 2 arrows, because we're showing our full arrows because we're showing the full movement of 2 electrons. And so here you now end up with this. This guy, and then of course in this case we have B minus, and so it's going to be now this B minus that's going to come in and attack our carbocation to give us to give us here our full reaction.
Dang!
Okay, so if you noticed on the last examples that we talked about, we were forming this carbocation where we had, if we were talking about H here, and two methyl groups and then a plus charge here, we now have this, what we refer to as a carbocation. And so this is going to form during these reactions. And so what we need to do is figure out whether it forms, does this carbon get the hydrogen, or does this carbon get the hydrogen, or does it even matter? And so it turns out that we have a rule that we can use to follow this, and this is what we call Markovnikov Markovnikov's rule. And so Markovnikov's rule basically states that the more stable carbocation will form. And so what is the more stable carbocation? Well, in general, we can say that tertiary carbocations are more stable than secondary carbocations, are more stable than primary carbocations, which are then more stable than methyl. Right, so for these reactions, this tertiary carbocation, usually what you're going to do is you're going to see secondary and tertiary mostly. These are the ones that will form, okay? So how do we go about
Drink it
applying
in.
this? Well, if we
Always
look
goes
now,
down smooth.
let's take, for instance, this compound, and let's draw this guy here. And so what we're going to do is we're going to treat this with HBr. And mechanistically, what we're going to do is we can see that, again, just like we had beforehand, we had the double bond, which is right here. This double bond is going to attack this this guy because we have a partial plus here on the hydrogen and a partial minus here on the bromine, and so our mechanism is going to move us from this way to this way. The bond here is going to break and go to the bromine. So this now is going to give us a separate, or a new structure here. But now we have to figure out, so which carbon is going to have the hydrogen? Is it going to be this carbon, or is it going to be this carbon? Which one has the hydrogen? Well, if you notice, I can draw a carbocation. If the hydrogen goes here, that would give me this carbocation right there at that point. Or I can draw the compound again and put the hydrogen here, and this would give me this carbocation. And so now the question becomes, which one is more stable? Well, if you look up to our chart that's up here, we can see the tertiary is more stable than secondary, which is more stable than primary. This carbocation right here is tertiary because we have three groups that are around it, right? We have one group, two groups, and this would be the third group that are carbons. So this is three alkyl groups, so this gives us a tertiary carbocation. And so it's this one that is formed. So this guy is the carbocation that we form. We don't form this carbocation. And then finally, the next thing that can happen is here we have our Br minus that was left over from our reaction that's over here. And then this is going to go and add right here to this carbocation, which of course we show with two arrows. And this gives us our final product that looks like this. And the H is just drawn for emphasis here, and typically in these skeletal structures, right, you're not going to draw them. Okay, so we can also have reactions with other types of reagents. So for instance, we can add water to a double bond. So um, the addition of water. So what we would do in this case is we might take some alkene and we're going to react it with something to add water to this, but we're going to need to break this alkene first, and so we're going to use some sort of concentrated acid. So one might draw H plus to indicate an acid here. All right. Except what really is H plus? Well, we might think of H plus in this case being H2SO4, so sulfuric acid would be the addition here. And so then we're going to add a little bit of water here to our reagent. So this guy is equal to H plus here. Okay? And so basically what you're going to see happening at this point is we're going to break the bond. So this double bond right here is going to get broken, and we're going to end up with this picking up the electrophile, which in this case is going to be this hydrogen, right? So once it picks up the hydrogen there, we're going to develop now a positive charge from the breaking of this bond right here. And so then now you have to decide if the positive charge is going to be on this carbon or is it going to be on this carbon right here. And we know that it's going to be on this carbon because this is going to follow Markovnikov's rule. So there's our positive charge. And the next step we can see, we can use water here to come in. So water will be our nucleophile. It has two lone pairs that are on this. And then basically the next thing that's going to happen is water is going to go and attack where the positive charge is. And so if water attacks there, we can draw this new structure. And I'm just going to flip it upside down like this. So here is now water. Now we're going to add water to this, but we can't have it hanging out with a charge on the oxygen, right? Oxygen doesn't want to be charged like this. So you're going to end up regenerating your acid. So how are you going to regenerate your acid? Well, remember, when you put H2SO4 in water, right, remember that this is a strong acid. And so you're going to dissociate completely into H3O plus and HSO4 minus, right? So remember that this is what we're going to have there, and so this H plus that we have is really H3O plus, and so now you can draw the ending part of the reaction where this guy comes over there and that guy comes down, and so now finally we have added water across our double bond. And so we end up with this guy. So we can also do the same reaction here. We can do this with an alcohol. So let me just draw a line. So we can essentially here, we can add an alcohol to a double bond. So if I take the same exact structure, so right here, and we're going to react this. Now we can't just add an alcohol right off the bat. So if I use this guy right here, so this would be ethanol, I still need some catalyst. So I'm going to need acid again. here. And so again, our H plus is going to be H2SO4, and the same exact process is going to take place where this guy is going to go and pick up that hydrogen, and I'm going to end up forming now a carbocation, right? And this time, instead of the water being a nucleophile, now my ethanol that I have here, because I'm doing this in ethanol, ethanol can be the nucleophile. So here we had water as the nucleophile up here. Now we're going to have ethanol here as this is going to be our nucleophile. Okay, so this will be our nucleophile, and with that, this is going to do exactly the same thing. The lone pair is going to come over here and attack where the positive charge is. And so now we need to draw the new structure. Again, I'm just going to draw it down here. And so now we have a plus charge. And so what do you think is going to happen? Well, remember, if we have H plus is going to be equal to H2SO4, and in solution you have H2SO4 minus, right? Or HSO4 minus. So let's just do this. We're going to regenerate our acid catalyst now at this point here to come and pick this guy up. And this can give us now an ether. This would be what we refer to as an ether, which has the general structure RO. Oops. The general structure R, or R prime can be the same as R or not. Now, I also need to mention that it is also okay at this point to have this happen. So this up here, or this. So either or is fine. There. Right, so this is how you can add water or an alcohol to a double bond. Okay, well now what if you don't want, in this case, so if we have our same starting material here, what if I want the alcohol to go here? Can I accomplish this? Yes, you can, and what you need to do is use what we call hydroboration. So hydroboration is going to use a boron. In this case, we're going to use borane, which is BH3, and it's going to complex to a solvent, which is THF. Right, so THF is simply tetrahydrofuran, and I'll just put this over here. So THF is equal to tetrahydrofuran, and it looks like this. Right, so that's the structure of THF, so let's just put this in a box up here. I'm not very good at drawing boxes, obviously, but so we're going to use this as our reagent, as our first reagent, so we're going to include a 1 here. And then the next thing we do is we need a second portion of our reagent, and so in a different pot, or either after this addition has been done. So we'll include the number 2 here to describe that. So this one will be OH minus, so something like sodium hydroxide, and then we will use, in this case, hydrogen peroxide and a little bit of water. Right, so what's going to happen here, if we look at this in detail, is that we're going to see that we're going to end up with this anti-Markovnikov addition. And that's because the OH is going to indeed go here at the less substituted. So the OH ends up on least hindered carbon. Okay, so what that means now is that we have to have some different mechanism that's going to happen here. We don't have the same mechanism that we've been showing. And so what we need in this case is for our boron to show us what's going on here. So if we draw out this guy, and what we can see is that boron, remember, boron has a empty p orbital, and so it is going to be Lewis acidic, and our mechanism is indeed going to be very different than what we had before. So the lone pair, or the pi electrons, are going to go from the double bond, are going to attack our boron, but at the same time the electrons from this are going to attack this bond that's in between the hydrogen and the boron, are going to attack this carbon. And so what we end up with is a syn addition. They're both going to come from the same face. Remember that a double bond is planar, it's flat, right? It has sp2 hybridization. And we're going to end up with this syn addition on the same face of our double bond. Now, what's going to happen is another one of these double bonds is going to react in the same way. Right? So we're going to get this other one that's going to do the exact same thing that this guy did until all of these guys right here are gone. So just put reacts until all H's are gone. Okay, so I'm just going to redraw this guy right here so that it makes it easier to show that. So I'll just do one over here. So let's put a hydrogen right here, and now we have our BH, and so right here can be our double bond. And so once again, this double bond is going to attack the boron, and this guy is going to come down here. And so now, to make things easier, I will just draw this guy. So now I have B, and I have an R group. And the R group, remember, is this alkyl chain right here. That's our R group. And then this is going to happen again, right? So until we get all BRs right here, right? So I'll just draw another arrow, and so we end up with this. R, I'm running out of room, so remember R is our chain. Okay, so here's our chain, and this is what's going to happen. Now, this is the first part of the reaction, okay? The first part of the reaction is done, and so now we need to move to number 2, the second part of our reaction. So in our second part of our reaction, now I'm just going to, what I'm going to do is I'm just going to draw B right here, and I'm going to put R here and an R here, and then I'm going to draw at the bottom our structure. Right, so this is this guy. Remember that all of these R's, again, are these guys. Right? Okay? And so now the next thing that's going to happen is I've got, if you notice, hydrogen peroxide right here, and I've got sodium or some hydroxide that's right here. Right? So what's going to happen in this case is I'm going to react hydrogen peroxide with sodium hydroxide, and I'm going to end up forming this guy right there. So now we end up with our OOH minus. Well, remember what we said about boron and the fact that boron has an empty p orbital. And so what's going to happen here at this point is that this guy right here is going to come over here and attack our boron. And this is where things tend to get a little bit tricky. And what we're going to do is boron, remember, doesn't want to have 4 bonds. And so it's going to end up wanting to get rid of one of these, because this now has a minus charge. And so what's going to happen at this point is one of these bonds is going to leave boron, and it happens to be this one, or one of the R groups. And if it attacks this oxygen, then it has to break this next bond. And so now what we have is this guy and O. Oops, sorry about that. Yes. O, and then 1, 2, 3, 4. Okay, this guy. And now our OH minus that we have in solution right here can come in and remove this, which forces this guy to be kicked out. And so just draw a down arrow here. And so now what we have is this OH, R, R, plus our O minus. And the next thing that can happen is, of course, we have water in solution. And this guy can regenerate our base right there, and we end up with our new alcohol, and this one is now anti-Markovnikov. So we'll just write AM, anti-Markovnikov. So that's how hydroboration works. This again, remember, this is going to happen right here. This is going to go 2 more times until all the R groups are gone, and this eventually ends up as BOH3. Okay?
No!